right. In the previous video, we've learned about the basic of chemical bonding, particularly in carbon. And we've learned about how the valence electrons, the four valence electrons of carbon, will adjust so as to give way for four types of bonding. And we've learned that the 2s2, 2p2 will now become a 2s1, 2p3, so that the other electron from the s will jump to the empty p orbital so as to give all half filled orbitals ready to be shared four times. And that is the reason why carbon can bond four times. It can be all single bond, it can be double double, it can be single single double, or it can be triple and single. That's the reason for it. And we also had in the previous video explained how the four terminal hydrogens will bond with the central carbon because your H has one S1. So each will have one S1 ready to be shared to this half filled single electron of carbon so that they can be paired. So it's just like pairing up, finding a partner. So as you will be filled, and you will be following the octet rule, and you will be stable, just like, seeking a partner. So that's really the concept of your sharing here. So that's the basic concept of your CH4. And we also discussed about how the S and the P will fuse and really come up with a stable structure of your compound. And you know that the answer why this is possible, why you have same angle length, bond length for each CH, and the bond angle of HCH are the same, it's because of the concept of hybridization. Now in hybridization, the S and P orbitals, even if their sizes are different, when they hybridize, they will form a very stable structure with hybridized orbitals. And the concept of hybridization is that all S and P atomic orbitals, well, not just S and P, the other orbitals also hybridize. But since we're talking about carbon here, it's just S and P atomic orbitals. They mix to create new hybrid orbitals. And take note that the number of new hybrid, sorry for the spelling, number of new hybrid orbitals is always equal to the number of atomic orbitals that were mixed. So if you have S and P atomic orbitals mixed, you get two new hybrid orbitals and you just combine them. How do you name them? Just name them as two S and P because you have one S and one P mixing together, so you call that sp hybrid. So each hybrid orbital is exactly like the other, and the geometry is based on this. So each is exactly the twin of the other. They're the same. If it's S and P, they look the same. And the geometry is based on the hybrid orbitals. When we talked about molecular geometry last in the previous lessons, we just count, diba? We count how many terminal atoms we have. And then we count how many lone pairs we have in the central atom. Basically, that's really the concept of your hybrid orbital. It's dependent on how many surrounding atoms you have because that's dependent on what will hybridize with your central atom. So that is the basis of your molecular geometry. Now, how do we exactly name the hybridization if there are more orbitals participating? So, if for example you have one S and two P, we call that sp2, and the 2 has to be a superscript indicating that you have two p orbitals hybridizing and one s. S is always 1 because it can just provide one orbital because it's S, it's spherical, it has one orientation. P can have a maximum of 3. D, if you exceed to D, that will be 5, and F up to 7. But again, our concern is just for carbon, then we will stop until sp3. We don't go all the way for D for now. So you have sp2 if they're one S and two P's, and then if you have one S, three P's, and one D, we call that sp3D hybridization. So that's just it. If you are given these terms or this symbolism, you have to know what it means. So it just gives you the quantity of how many orbitals are hybridizing. So what geometry, what shape could you expect from the hybridization here? If it's sp2, sp2 is a total of three hybrids. So that's like it can either be three bonding pairs or two bonding pairs and one lone pair in your central atom. So the basic molecular geometry for that is a trigonal planar for three bonding pairs. If it's two bonding pair and one lone pair, you get a bench shape, if you recall that. If it's five hybrids, it can be five bonding pairs, all of it, with zero lone pairs, so you get a trigonal, bipyramidal. If it's four bonding pairs and one lone pair, that's going to be your trigonal pyramidal. Your three bonding pairs and two lone pairs, you can have, two lone pairs and two bonding pairs, that you can have a bench shape again. And two bonding pairs and three lone pairs, you will get a linear. So this is dependent on your molecular geometry. However, we're not focusing too much on your molecular shapes here. We're focusing more on the hybridization of carbon. So, how do we go from here? How do we make use of our knowledge on hybridization to carbon? So, in actual, this is how it looks like, the hybridization. These are sample hybridization of ammonia, NH3, and your water, which is bent. NH3 is a trigonal pyramidal with one lone pair on the other side. So this is how it looks like. It looks like a cloud. It really represents your electron cloud. They hybridize perfectly, and you won't see anymore where's the S and the P in the final output, because you have a stable molecule. So that's how you imagine your molecule when they hybridize. As for carbon, this is how we summarize everything for carbon hybridization. Now, you have here in the table, it says that coordination number of carbon atom, the type of hybridization, and the geometry. That's the shapes, the possible shapes you can have for any carbon, related hybridization. So when we say coordination number, it means how many orbitals are bonding. So it's dependent on how many surrounding atoms you have. So if you have four surrounding atoms, just like the CH4 I showed you, it's going to be an sp3, one from S and three from the p orbitals. So a total of four. That's why you have four terminal atoms. So S will, all the S's, the S will not necessarily S. One S from the carbon and the three P's will all share. They will all share, forming to share with four surrounding atoms. So that's why you'll get 4 0. A 4 0 will have a shape of tetrahedral. So again, one S from carbon and all the three single or half filled orbitals of carbon will all share to all four terminal atoms. The next type of hybridization is when you have only three terminal atoms. And when you have three terminal atoms, only three from carbon will participate, one S and two P's. Now, you might ask, Madam, what will happen to the other available P? What will it do? There's something that's going to happen, which I will show in the next series of this video. It's all about the sigma and the pi bonds. Now, remember, when you have three terminal atoms, this is the time that you'll have a double bond. And there's a mechanism for a double bond bonding or sharing, which I will discuss again in the next series. You watch out for that. So for three terminal atoms, you'll only have sp2, one from S and two from P. That's why, to accommodate the three surrounding atoms. So you get a trigonal planar. Sorry for that. It should be trigonal planar shape. And lastly, if you only have two surrounding atoms, then only one from S and one from P for carbon will hybridize, will share, and so you will get only a linear shape. So, Madam, what will happen to the other two of P? There is a mechanism for that. This happens actually when you have triple bonds. And when you have triple bonds, you get some pi bonds and sigma bonds as well. So that's it. Summarizing hybridization for carbon, because we're focusing on organic compounds. So this is the summary of all the hybridization you will expect for carbon. So you have sp3, sp2, and sp with 4, 3, and 2 coordination numbers respectively. So that's it for now. Watch out for the next series about sigma and pi bonds. Bye. God bless you.